Thank you very much for the possibility to give again the talk here at the Institute, where I really feel like at home already. So, as Nima correctly noticed, this subject was presented already like 2 years ago here. So some people probably will recognize all transparencies. All people recognize some transparencies, but hopefully not all people recognize all transparencies. No, no, there should be something new in it if the list of references doubled. Okay, so the motivation is n equals 4 super-Young-Mills theory as an example of sort of phenomenologically interesting theory, because it is well defined for any coupling and from IR to UV all the way, and also it has a rich space of rich moduli space, flat vacuum. And unfortunately, no supersymmetric theories of this kind are known in 4 dimensions, which is always a mystery to me. I keep on interviewing knowledgeable people why it is so that we don't have a non-supersymmetric theory with such properties. Maybe there is a theorem about it. Exactly. At least we know Banks-Zaks theory, but these are isolated points, yes. But to get really flat vacuum which are stable quantum mechanically, that's something which nobody knows probably in 4 dimensions.
You're happy at large n, you can take orbifold
and then there will be flat vacuum, and it's non-supersymmetric. Interesting. And is it unitary?
Yeah.
Okay, then maybe you.
Yeah.
Here, of course, I also will pretend that so actually I will describe gamma-deformed super-Young-Mills, n equals 4 super-Young-Mills. The supersymmetry is completely broken, but it is not CFT anymore normally, because the double trace couplings are generated and they start running. But one could tune them to a fixed point, or rather fixed line, because everything is all these couplings are functions of Young-Mills coupling, which is not running. And one can get still CFT, but this CFT will be already non-unitary, because the fixed lines will be complex, and it's logarithmic CFT that we know already. But remarkably, it's still integrable at this special tuning of couplings, even double trace couplings. It's still integrable, and it can be described by what we call now this formalism of quantum spectral curve, which we introduced some time ago for the computation of the spectra of anomalous dimensions in n equals 4 super-Young-Mills. So it works with gamma deformation as well, and it's still a quite so integrability and ADS-CFT duality are interrelated for sure, but both stay a little bit mysterious. Both phenomena stay mysterious, and that's why we proposed once with Omer Gurdogan a special double scaling limit of gamma deformed n equals 4 Young-Mills, which combines strong imaginary gamma deformation, already smells like non-unitary, and weak coupling. The result was so-called fishnet CFT, which is dominated by planar graphs. In the simplest one single coupling version, it's dominated by these fishnets, which have been introduced by the Molochikovs and have been understood that as integrable statistical mechanical model, which can be described by SO2, D conformal spin chain, non-compact conformal spin chain. This fishnet CFT can be generalized to any dimension. That's why I speak about arbitrary D. But of course, it doesn't have its at any D. It doesn't have its mother theory, the corresponding super young mills, not that, at least that I know any. Okay, so this is a little introduction. And now, what is gamma-twisted super young mills? I remind quickly. Here is the usual young mills with 3 complex scalars, 3 complex fermions, gluons, gauge fields, gauginos. And you see a bunch of commutators here, of course, in the interaction terms. Then gamma twisting is essentially a sort of a star product. In each such term, the matrix fields, various matrix fields, come in different orders. And the rule is that once you change the order of the fields, you put a special weight for this change, where Q depends on the charges, QAB depends on the charges of fields A and B, and you introduce the gamma parameters, 3 gamma twists, in such a way that if you exchange AB to BA, Q goes to 1 over Q because it's antisymmetric here. J's are Cartan charges of R symmetry. Okay, then from practical point of view, you simply exchange usual commutators by Q commutators. So you, the commutator, Q commutator is defined in this way. And, then if you gamma twist the action, you simply decorate by Q's all the commutators. Okay, then this R symmetry is completely broken, of course, and the superconformal symmetry, of course, the conformal group stays intact in principle, and you have U1 cube symmetry left from R symmetry. And now I wanted to demonstrate that, in fact, this deformation is a topological deformation on the planar graph, on each planar graph. Suppose we are on cylindric graph, and then this produces sort of quasi-periodic boundary conditions. Let's demonstrate it. So let's pick up one term. Now I say phi1, phi2, I call Z and X, complex fields. Then if you consider the corresponding commutator, you will encounter 6 terms. I mean, for this particular term, I took only one term out of all this sum. And if you do Q deformation, only these 2 terms acquire some factors, Q square and 1 over Q square, the rest known. And if you look at the corresponding vertices, you see that you have always a vertex where you have blue line of Z propagator with arrow because it's a complex field. It goes from Z to Z bar, from X to X bar. So if they cross, you get some factor. If they cross in such a way that it's clockwise, say from blue to red clockwise, you get Q square. If it's anti-clockwise, then it's Q minus 2. You can call this vertex chiral and this anti-chiral. Then if the fields X and Z just scatter like this in the color space, you don't have any factors. So then let's look at some configuration of some graph. Suppose you have a line of propagators, blue line of Z field, and some red lines of X propagators crossing it. And in fact, you see that you simply take a product of these Q's and Q square and Q minus 2, and at the end you get the number of vertices where you cross in one direction minus the number of vertices when you cross in another direction. So it's sort of, you can cut this cylindric graph along the cycle to open it, and you can insert some line of defects to accounting for this twist. And then, as I was taught even being PhD, that once you encounter a new parameter in the theory, you try to send it somewhere to infinity, to I infinity, etc., and see what happens. I'm surprised that nobody before did it here. And you see that, for example, you drop this. If you send Q to infinity, you drop this anti-chiral vertex, and you stay with chiral vertex. And since G square multiplies Q square, so you can play with the double limit to kill all these vertices except one and stay finite still. Or vice versa, you can send Q to 0, which is the same, but you exchange chiral and anti-chiral, very similar theories. Okay, that is essentially what is, okay. And then you can play with these Qs to sort of peel off your graph from some of the fields, like gauge fields or etc., and to stay inside with something much simpler. And this kind of lemon already suggests a structure quite similar to what we will get inside. Okay, so playing with these boundary factors, you can just peel your graph and drop away some fields, some big portions of graphs. Yes?
Why would you need G equals to 0? Looks like Q equals to 0.
G equals to 0? Because it will blow up otherwise, yes? If Q goes to infinity, you have an infinite coupling. Okay, then in the simplest, then this double scaling limit means that you send all three xi's to I infinity, G to 0, and you keep xi, all three gammas, sorry, to I infinity, and you keep xi finite, G times this twist factor fixed. So you get three couplings. Do I do? Now, here is the action which is left. Essentially, you drop all halves of commutators, and you stay with the vertices which are chiral. You dropped all anti-chiral vertices. Here is the action. This is the full model which we proposed in this early paper, which contains 3 fermions, 3 bosons. So gauge fields go away and gauge inner because they don't carry R symmetry indices. So you have this sort of already much less complicated theory.
I thought you were only keeping one word.
You could, but this is the most general one, and I wanted to discuss this one. This is, of course, this is not new. It's already, we invented.
C2 and C3 are much smaller than C1. You just keep one word.
Yeah, later I will on the next transparency, but I want to discuss the general fishnet because it already shows really its fishnet properties. And I want to discuss the Feynman graphs of this theory. Namely, a generic Feynman graphs can be constructed, as we showed in a paper of a couple of years ago, already after my talk here. Oh, it was even, okay. So you start with 3 types of lines of propagators, like for each of 3 colors. You have 3 colors here. So suppose they cross in all possible ways. If you fix the boundary of this graph, like you fix maybe single trace product here, so you get a set of graphs which can change only by moving, say you can move this line through this vertex, it will change a little bit, so you can move a little bit these lines, but the structure should be like this. Now, you decorate each line, a piece of it will be scalar field when it's solid, and if you continue with dotted line, this is fermionic line, already the line on fermionic propagators. And the line should be, of course, closed, like this. Both fermionic and bosonic lines are closed because each U1 is conserved. Yes? And now, of course, you get strange. Of course, if 2 solid lines cross, this means you have just one of these 3 vertices, the 4 scalar vertices. But if fermionic line crosses bosonic or fermionic with fermionic, you simply, like here there are a few such cases, you simply disentangle them by using the Yukawa vertices. Each each 4 vertex you can represent as two Yukawa vertices, yes. And what is, say, here or there, and what is nice here that it's already, you can do it in a unique way. Once you draw this skeleton graph and you fix the order of crossings of lines, it's the only way to disentangle it with this vertex. So you see, we call it dynamical fishnet. So you have some degree of freedom where these lines can move a little bit across the vertices, each of 3 sets of lines. But after that, it's fixed. This is the graph, the most general graph of this double scale theory. And of course, the question arises, what is the integrability here? What is the spin chain with these strange movements? I think it could be an interesting point that this is a new integrable, lattice integrable models with sort of dynamics. Your spins can move across each other. And it could be another step towards understanding the n=4 super-Yang-Mills integrability also. But we tried a little bit, we didn't manage to understand what is integrability here. Apart from maybe if you blow up, you can play with this size and stay only with Yukawa interactions, drop all these interactions. Then again, you can get that kind of the hexagonal graphs, regular hexagonal graphs with manifest integrability, but not for this general model. Now I go to this case of one.
Sorry, the conclusion. Is there supposed to be some, like, is there some subgroup of the Yangian that's left unbroken by this or not?
Yes, we tried actually. Yeah, we tried hard, maybe not hard enough, and we couldn't find the same nice Jungian symmetry as for single fishnet graph, which I will quickly discuss in a moment. I wanted to raise this point, but you sort of you have foreseen this question. Okay.
In what sense is it the CFT?
It is a CFT, although non-unitary or logarithmic. I wrote the action. I can compute correlators, and I know that this is conformal. Actually, at any value of this G or gamma, this is a conformal theory if I tune to the double traces to the fixed point. That we have a lot of evidence for it. But indeed, it's not unitary. For example, it will for sure generate double trace terms, which I don't put here. Okay, now the biscalar theory. Here I tune only one single coupling, say Xi3, which I call Xi here. Then, as you see here, all terms die except one. This one, because Xi1, Xi2 I put to 0. So all these terms die because they contain it. And of course, you stay only with this chiral term. The perturbation theory, 4-dimensional perturbation theory, consists of standard massless propagators plus this chiral vertex with, say, clockwise, by definition, orientation, and the anti-chiral vertex should be dropped. Now, it's evident that this complicated dynamical fishnet becomes usual fishnet with rigid square lattice structure, because you drop all fermions, you drop one system of the lines, it's everything which is left here. And it's easy to think a little bit and understand that inside big graph with fixed boundary, only this graph is possible. You cannot turn back, for example, with the blue arrow. You immediately you will immediately encounter this kind of anti-chiral vertex, which is not present there. And there is no mass or vertex renormalization in this theory, so the coupling Xi doesn't run. For example, if you look at the mass renormalization, you have one chiral, one anti-chiral vertex, so you should drop this. And you have double trace terms. generated by, for example, this graph. These terms are generated by this kind of graph, which looks non-planar, but still this trace term contributes even in the leading order. And then you can really, we worked it out in various papers. Say, I don't cite it here, but we, with Korchemsky, Grabner and Gromov, we worked out how alpha 1 depends on Xi in order to be on the critical line, and alpha 2 is essentially Xi square. It is enough to put it to Xi square to be at criticality. But alpha 1 is sort of, it contains complexities, so it's a complex critical line. Okay, now let's study this theory. And the first thing, which is new, not presented 2 years ago, last year we found that this theory has flat vacua. So there is no supersymmetry, but it does have flat vacua which are not lifted by quantum effects. Of course, it's all very exotic, esoteric, I would say, but still, it does exist as a phenomenon. So, as usual, what you have to do, you have to expand your fields around some averages, which don't average values, which don't depend on x, and the effective action, which we find is depends on these averages, of course, and plus there is a standard term because you generate masses by this shift. There is a standard term of the type trace m4 log m square over mu square, which is well known in this Coleman-Weinberg theory, where m is the mass matrix consisting of these averages. So essentially, this is a vacuum loop, which contributes here with mass term inserted somewhere. And the first term is the full action, single trace term and double trace terms. Okay, so now what is nice here, there are no multi-loop corrections to the vacuum. No such planar graphs which correct this one loop. So it's one loop Coleman-Weinberg potential appears to be exact. Just to demonstrate it, but say for some graphs, let's try to look at this graph where you have loops of, say here you have x field, you have z field, and of course they should be closed. For the vacuum loops, there should be closed loop, but you cannot draw planar system of closed intersecting loops where you don't have, no, essentially each loop intersects with each by at least two vertices. One of them is chiral, another anti-chiral. If you draw arrows, you always have chiral and anti-chiral crossings. So all this system simply doesn't, all these graphs simply do not exist in this theory.
That's only planar.
That's only planar, yes. Unfortunately, we don't know much about non-planar theory. Again, maybe it's like, this is an example where I know next to nothing about finite n here. Maybe this CFT exists at finite n somewhere in complex space of couplings, but okay. And now we look for flat vacuum. Of course, it should obey the classical equations of motion for averages. Like it should be a minimum. And a simple example of such a flat vacuum would be when the first field, one of two fields, is simply put to 0, and the second is taken diagonal such that trace of its square is 0. Of course, it's a complex field, so we can always find such diagonal fields that the square is 0. The mass term, this mass term, is essentially the direct product of these two diagonals, and V is the mass parameter. Okay, a possible choice, for example, is to take SUN over 4 to the power 4 pattern where you have these quartets of 4 numbers repeating at the diagonal n over 4 times. And unimodularity imposes 0 of their sum. Then classical part should be 0. It's simply sum of them is 0. This is this condition. And then the quantum, if you take into account the quantum part, you have to also to obey this kind of relation, and you happily find the solution of them. Z4 is just a normalization because they are homogeneous. You choose it to -1, and then you find some solution. So it's a pattern of spontaneous symmetry breaking. Of course, everything is complex, as you see, and you don't want to say, of course, that this is the stable saddle point. But I think it's a good example to learn something about spontaneous symmetry breaking in conformal field theories. It could be a nice toy model for that. Is it integrable at broken vacuum? No idea. Okay, so this is about the existence of quantum modular space. Okay, now Jungian symmetry, this is an old result, so a brief review is that you take so single trace correlator consisting of these 4 fields, phi 1 bar, phi 2 bar. I keep changing the notations, sorry. So these guys are one of these 2 fields. Then such correlator actually is defined by one single graph, planar graph. So you simply take these external fields and attach, connect with the correlators. Every order of these fields produces particular graph, and it's Fishnet graph. Inside it is regular square lattice. And all these graphs can be classified by just cutting out of a sheet of square checkered paper a disk along some boundary. Okay, you can, in principle, generalize it a little bit and take multi-sheet sort of branching surface, and then you can cut even more the disks with more sophisticated boundaries. But that's everything. You have always one graph. And then we found that then the dual graph with light-like momenta, like you take momentum pi, which is a difference of you take xi, pi, which is a difference of 2 x's, xi minus xi plus 1 on the light cone, and you get amplitude in an appropriate limit. And this amplitude, or even this single trace correlator, they are finite and duly conformal invariant explicitly, and they obey Jungian symmetry, as we noticed a couple of years ago. Namely, so it's the dream about the full n equals 4 Young mills comes true here because of the simplicity of this limit. So you can analyze a particular graph. What you do, you introduce conformal Lax operator. So you have 4x4 matrix L alpha beta, which is U plus generators of SU4, just fundamental generators, times generators of conformal group. You sum up over AB over the labels of generators. And so this is the space of conformal group, and this space crossing it is this 4x4 matrix.
The simplest graph you'd have would be a box with 8 external legs, or
with 4 even, just this standard cross, which obeys.
Not finite. That's divergent. I'm confused. You said everything is finite.
As a single trace correlator, it is not divergent. I mean, if you fix all 4 points, it's not divergent.
Is the diagram
just cross with 4 fixed points.
But if
The-
the points are null separated, that's not finite. When you integrate it, it's not finite. I thought you wanted the consecutive points to be null separated.
That's true that you can get these collinear singularities, so I should be careful. The statement is about correlator. Then you have to go to this light cone limit carefully. There could be some singularities. But I remember we had some statements about that it works smoothly and you can really generalize to this limit.
I mean, there are many things which are definitely fine.
Mhm.
I was just wondering about that simplest case, whether you're even talking about the box. Anyway, that's fine.
Yeah, but each of these graphs is finite if you separate the points. That's
If they're not null separated.
if they are not null separated. That just yes, not null separated. Yes, that's why it's good to study it. And then you take you have dimension of representation and spectral parameter u. You fix 2 combinations, u plus, u minus, out of them, and you organize the monodromy around the graph. You act at each leg by these conformal generators in conformal space, and you multiply them along the path in this 4 by 4 matrix space. And you change appropriately u plus, u minus. Every time you turn to the right, you add 1 unit to each u plus, u minus. If you turn right, you subtract. So, and the claim is that you can. So the graph itself is the eigenfunction of such monodromy. So that if you act by such monodromy on the graph, by integrating over all intermediate coordinates, you get same graph with some simply calculable eigenvalue, which consists of this u plus delta. Delta changes. I mean, delta corresponds to these integers. And if you expand in u, you get differential equations on your graph, a set of differential equations which normally defines completely the graph, but they are not easy to solve, although they are linear, they are not easy to solve, of course. Okay, and the question is whether, as Nima already pointed out, the question is whether the full dynamical Fishnet graphs have this conformal invariance, even after summing up inside the disk all these shifts of lines. I can, for example, I can move this line through this crossing, and it will be another graph. So I can move all these lines, but even fixing the external legs. So there is some trivial sum over graphs. The rest is completely fixed. Okay, so this is.
Sorry, this was true before. This is true even when the consecutive axes are not null separated, or they need to be null separated.
This thing, in principle, yeah, we formulated it after even this limit of null.
But is it true before? Or no,
all this is rigorously true before.
Oh, right, right.
But some things can be said also about the amplitudes, not only correlator. Okay, now next, operators, correlators, and the related graphs. So the most general local operators in this biscalar Fishnet theory are of this type. Yes, you mix up phi1, phi2, phi1 bar, phi2 bar.
Sorry, that was just
derivatives.
SU2, 2. Sorry, I apologize. That was just the ordinary, the usual SU2, 2 bosonic Yankee.
You mean
The thing that you talked about, your Lax operator and stuff. That there. Yeah.
This one?
Yeah.
No, this one.
No. I mean the simpler one.
The simpler one. It's just biscalar theory, 2 scalars.
But which Jungian symmetry is real?
Which Jungian symmetry?
SU2, 2, bosonic SU2, 2.
Yes, yes. You see, I take the generators in this representation, 0, delta 0. So with zero conformal spins.
I thought you said earlier that you had a capital D for space-time dimension before. Is there something
This acts in the space of space-time dimensions. These generators act on the legs of the graphs, on the graph, which are fixed points in the space-time.
For any number of space-time dimensions, you always have
Here it's for 4 dimensions, but I'm pretty sure, yeah, the same picture, the same graph picture, of course, exists at any d dimension because it's just a topology of graphs, and I'm pretty sure that it's generalizable to SU d, comma 2, 2, comma d, almost directly. And in the paper which this is a nice paper of Chicherin, Derkachov, Isaev, where this kind of flux presented for any d. Nobody worked it out, but I'm pretty sure it's a direct generalization. What is nice also, there is a special limit to Lipatov type, BFKL type physics here. These models are, I will speak about it slightly later. Okay, now I speak about local operators and the computation of anomalous dimensions. So let's take just a mixture of phi1 and phi2 without derivatives and phi bars. Actually, adding phi bars creates some mess here because suddenly some operators become protected, some not, and we worked on it we discussed it for quite a long time with Joao, and there is no full picture for this kind of operators. But for this kind of operators we call Magnon operators, when you have phi 1s and somewhere you have phi 2 here and there, and the task is to calculate correlators, the anomalous dimensions, which are, of course, encoded into 2-point correlators. So we compute anomalous dimensions as functions of coupling psi. And already it's easy to understand that this trace phi 1 to the L operator, which would be a BMN vacuum in the full theory, in non-deformed theory, becomes renormalized by wheel type graphs, and this is the only type. And if you compute this graph, which is a very tedious problem to compute it, even for, you have m frames. For 1 frame it's easy. For 2 frames already it's integrability. It's a complicated thing, but you can compute it up to two frames. And then by standard RG formulas, you can compute from here the anomalous dimension of this operator up to, in this order. Then if you introduce magnons, wheels become spirals, even multi-spirals. Phi 2s create lines which are winding around. If there are 2, there are double spirals, etc., etc. And this is another set of graphs which is not yet well studied, although some results. It's also integrable, this graph. Okay, and the dimensions can be computed due to integrability using integrability of gamma-twisted n equals 4 super young mills by trying to send in corresponding equations to achieve the double scaling limit. And I wanted, probably I will not go to the end of my transparencies, but I still want to present here the last, the ultimate picture of the integrability of quantum spectral curve, which solves the spectral problem in n equals 4 super young mills. Because to me, it looks already, the whole scheme looks ridiculously simple, and on 2 transparencies, I want to present it. Although I presented it here already like 6 years ago, but it's a new, sort of new setting. Okay, with gamma twist, also with twisted case. So.
Can you say again, why is the fishnet CFP a CFP? I didn't really get the answer. Show that a beta function dimension?
It's, of course, already you observe it, for example, on Feynman graphs, because the graphs are conformal. Each graph, fishnet graph, is a conformal object. But maybe it's not enough, because you can have various anomalies, like you generate double trace terms.
At the planar level, right?
On the planar level, yes.
So I think the idea is that you can't draw planar diagrams with these limited vertices that would correct the 2 or 3 point function. Is it as simple as that?
You can what?
Well, it's hard to construct planar fishnet diagrams without a lot of external lines. So there probably simply aren't any that are supposed
No,
to.
you can construct, for example, 3-point functions, and people have studied it.
Isn't it only very limited diagrams?
Of course, there are not many of them, but already if you fix 3 points, there are a bit more of diagrams. I will, if I go to the end, I will speak about 4-point functions, even you'll see how.
For the 3-point function, are there only finitely many diagrams? Or is it
It's in each other, it's always finitely many. I mean, in each other, it's by definition finitely many, but very, very few.
And this question was to all orders.
Yeah.
Then we don't, well, I'm left agreeing, disagreeing, but I don't
No,
know.
but each of these diagrams is conformal, first of all.
How do you prove that?
That's already by power counting, of course, you prove it easily because you have massless propagators, and you see that it doesn't have scale, the graph, with this kind of propagators. Of course, it's not enough. You can, for example, you can build, for example, you build a cylinder out of repeating the same structure many times and generating the graph by so-called graph building operator. This operator is conformal. You can easily check it. Just you do conformal transformation, and all conformal transformation. But it's not enough, I agree. There are divergences which somehow are fixed by double trace terms if you tune them, and then everything works like.
I thought you would say that you can't really make cylinders that contribute to the 3 or 4-point function.
Yes.
They're too restricted. And that was why there were no divergences. Maybe that's too naive. Anyway, go ahead.
No, it's okay. Maybe if I go to the end, there is some explanation. No. My point is that you take gamma deformed n equals 4 Young-Mills. It's not conformal if you take the gamma parameters real. Of course, it's not conformal. Double trace coupling run. But if you tune double trace coupling to necessarily complex fixed point, you have complex conjugate fixed points, then it's conformal. And then it's described by quantum spectral curve, which I will describe now.
Tell us that at the planar level, it was always conformal, even without the double scaling. That's not the case.
But gamma deformation introduces running terms, the double trace terms. So it's a subtle question.
At the planar level, right?
Even on the planar level, double trace terms are relevant in the planar, in the leading order. So you have to take them into account. And somehow they are needed to fix, to cancel the singularities. But there is also a general belief that for any value of these parameters, including this limit, you have conformal theory because quantum spectral curve works so beautifully for this case. So we suppose that it describes this limit as well. So okay, so what is quantum spectral curve? You introduce. Oh, sorry. I keep fixing it in every talk, but I forget. I still copied it. No, of course, CFT4. So we introduce a set of so-called Boxter functions of spectral parameter U, labeled by multi-index I, which I will describe now. And this index can be described by the labeling can be described by so-called Hasse diagram, which is for the JL type algebras, JLn type algebras, and n hypercube. For example, for JL2, you have Q empty set in one corner. Then its neighbors are Q1 and Q2. In spin chains, there are two solutions of second-order Boxter equation, for example. And then at the end, you have full set Q1, 2, which is which you impose, by the way, for spin chains like U to the length at something like that. Okay, then if you increase the rank, same picture, you have three-dimensional hypercube. You have nearest neighbors for Q1, Q2, Q3. Then, for example, these two converge to Q1, 2 from Q2, Q1, etc., up to the full set. JL4, the four-dimensional hypercube. And Then you introduce the following structure. All these functions are not independent. So there are 2 to the n Q functions, but they're not independent. You introduce the main diagonal somewhere going from Q empty set to Q full set. And in each phase, two-dimensional, two-phase, you introduce the following relation. Say, along the diagonal, if you orient, this square is oriented along this diagonal, you have the following condition, that the product QB, QD along this diagonal is the Wronskian determinant of QA, QC, whatever they are here, whatever the numbers are here, which is, you know, these Q functions with shift plus I over 2 and minus I over 2. And this introduces a Grassmannian structure in the space of Q functions. Essentially, if you fix Q naught, say, to 1, it's just normalization, then you can express all other Q functions through single index Q functions, say here through Q1, Q2, Q3. Okay, this is the structure which is the nicest way, in my opinion, to describe the integrable spin chains. The beta ansatz equations follow immediately, etc. But we want to go for ADS CFT. Now, what we should do, we should introduce the hypercube of dimension 8, which is this mess, 256 vertices. And because the rank of your group, of your supergroup, is 8, yes, 4 plus 4, PSU 2,2/4. And then you have also this Grassmannian structure, which I described. But to make it supersymmetric, you have actually to fix not this and that function, but the opposite function. For JL4/4, you, for example, can fix this function to 1, this to something, and solve this set of equations through the single index, from the functions which are neighboring to this vertex. This is supersymmetrization in the simplest possible way in spin chains. So if you want JL4/4, you take this diagonal. If you want JL3/5, you take this diagonal. Yes, 3 units here, 5 here, etc. So the passage from usual spin chains to super spin chains is very transparent here. Okay, and now I declare that the same structure of Q functions we have in n equals 4 superior mills for any coupling, etc. And we want now to fix the analytic structure. This was algebraic structure. We want to fix analytic structure. And here we start again from this hypercube, 8-dimensional hypercube, and we fix these 2 vertices. We fix them to 1. This is the first step. This and that are put to 1. And then you have special functions. So let's look at the looking glass here in the vicinity of this vertex. You have 4 functions which we call Pj, single index function, and these ones which we call Qj, 4 plus 4. And then there are Hodge dual functions on the opposite, diagonally opposite, Q with upper index from 1 to 4, and P with upper index also. These functions are the most important to formulate the problem. And namely, what we do, we first fix large U asymptotics, large U asymptotics of all these functions. It's always fixed through Cartan charges of given state, of given operator. Say for P, we have, I don't give, we have this power-like asymptotics with various, for various values of index B, various sets of plus minus J's. All this is group theory. And also these Q's are some combinations, products of our e to the gamma factors, e to the I gamma factors. So, so this is the only place where the deformation factors, gamma deformation factors enter. And then they have also, on the main physical sheet, these functions have one single cut. So they have this asymptotics and one single cut which goes from minus to G, where G is the Young-Mills coupling, the only place where Young-Mills coupling enters to this business. And nothing else, no other singularities. For Q functions, it's almost the same, but they describe rather the ADS part, conformal part of the asymptotics are fixed by conformal charges. Instead of the shortcut, you have long cut, which goes through infinity, but otherwise it's the same. So that's it. We fixed the analytic structure. The only thing which is left is to find some monodromy, which relates what do we see when we go under the cut. And here there are very nice relations which which stem from even classical spectral curve. You relate these Q functions to that Q functions. For example, Q1, these functions to complex conjugate of that functions. Q1 is related to Q2 with upper index, so Hodge dual bar, etc. A couple of these relations are enough to fix everything, even not all of them. And that's it. This is the formulation of spectral problem in n equals 4 Young-Mills, even gamma deformed. It's left only to solve it and to fix delta of G square with given charges, with given set of charges, and normally you discover there a discrete spectrum of anomalous dimensions. And it's a huge business already. Say, I simply flashed with some results. Say, Konishi dimension was computed up to very high. We computed even in our original paper with Gromov and Viera using old-fashioned method of thermodynamic beta ansatz and our Y system, which we discovered as exact solution. Okay, strong coupling is not yet a finished business. It's much more complicated than weak coupling, where we know when we can algorithmically generate results for example, for Konishi, this is 11 loops from these papers. It's 11th loop even, given all in terms of zeta numbers. And this beautiful picture of from the works of Gromov and collaborators, he invented an ingenious numerical way to to solve this quantum spherical curve up to 50 orders, 100 orders, whenever you want of precision. And for example, here is the dimension, real and imaginary parts of dimension of this operator, the twist 2 operator with S continuously, analytically continued to all complex values, which is it was important business compared, for example, with old papers of Polchinski, Strasser. But this is the precise picture and exact, more or less. Okay, so I wanted only to give a little review, and I have 5 minutes left for something. Then I only tell you that there was in our work, we went to this double scaling limit and derived from quantum spectral curve already the equations for fishnet, which was quite tedious because it's difficult to make G square and twist factor meeting in the same equation and then go to double scaling limit. So this coupling appears to be here. Okay, then I don't want maybe to spend much time here. Gluing conditions become something like this for two solutions of this equation. So, and at the end we extracted information about these planar graphs. For example, this 12th order of this wheel with 3 spokes, and also some numerics, which is of course very precise.
Is this a set of graphs for which there's some nice coaction?
Coaction? What is coaction?
I mean, like a la Panzer ground it all. I mean, is there some? They're all multi-zeta values. So is there an understood Hopf algebra structure associated with these graphs?
That I'm not familiar with. Actually, no, I'm not I tried to learn something about computing these graphs. For example, this graph was computed by Eric Panzer, and it was already a very sophisticated, very sophisticated calculation. I mean, by this integration by parts and etc. The theory probably you speak about, but we reproduced it, of course, and now we can generate from integrability many more these graphs. Okay. Now I wanted to, in the last 3 minutes, hopefully 5, I wanted to speak about our last result. It's by scalar fishnet. Oh no, that I wanted to introduce CFT at any d. You introduce it by this formula. So it's the same action except that you take Laplacian here in any power delta and this Laplacian in d over 2 minus delta, which tunes your graph to conformal. Because then it's fishnet because it's the same structure of chiral vertex, but the propagators are such that the whole graph is conformal. It's dimensionless, and then one can even check that some conformality transformations on the boundary prove that it's conformal. It is related to integrability. Why it's what?
Are you sure that there are no divergences inside?
No, there are logarithmic divergences, of course, but no, it depends on what you do from this graph. The boundary also matters. For example, if you do a cylinder, there will be divergences. Or if you do the wheel, I've showed that there are 1 over epsilon.
Very small wheel, right?
Very
Oh, I see.
For example, for the wheels, the number of frames in this wheel gives you 1 over epsilon to the number of frames, the divergency. But then it's precisely what you need for computing the, when you compute the dimension, it's precisely boils down to.
What's not clear, you must have divergences in order to produce a number.
Of course.
But then, is it clear that there are no divergences that you introduce other couplings? And perhaps a coefficient?
No, it always worked. I don't know how to answer directly on your question, but
The simplest thing you're saying is that with this, the fine rules of this Lagrangian gives you graphs that are conformal, that are conformally.
that's one thing. But you can prove it only on particular sets of graphs. For example, for cylindric graph, I can certainly prove it. The layer by layer, I can prove that this operator which creates it is conformal. And this is actually a conformal spin chain. It's non-compact conformal spin chain. So everything looks perfect there. But if you start looking for example, 3-point functions, you might ask this question. But then we should trust the belief that n equals 4, even gamma deformed, is conformal. So all this, in principle, should be embedded into n equals 4 Young-Mills, including.
N equals 4, there's separate arguments.
D, it's true that if D is not 4, then it comes from nowhere, yes. Then, of course, I wouldn't guarantee, but I think it should be also, it should work also as conformal theory. I agree indeed that it should be proven or somehow motivated that if you take multi-point functions, why should it be conformal? But we have some examples.
Let me be more concrete. If I take this at face value, let's just substitute D equals 2 and delta equals 1.
Mm-hmm.
So I think one of them is dimension 1, and the other is dimension 0.
Yeah.
So there are lots of relevant operators.
Okay.
So you have to argue that they're not Young-Mills. Well, let's just substitute. I do follow the rest. D equals 2, delta equals 1. So the first term is a canonical kinetic term, 2 dimensions.
Yes.
The second has no the exponent is 0.
You mean this and that? But of course, the powers are chosen in such a way that the graph is conformal, that the graph has no dimension. I agree that there are divergences and there could be anomalies, etc. But it was never noticed. For example, where we really have done calculation, it's the wheel with 2 spokes only. And even 4-point function. So you have two sort of rails, and then these frames around, and you have 4-point function. This is perfectly conformal, and the double trace terms conspire to cancel the dangerous divergences at the critical point, precisely where beta function is 0. It works for any dimension d, for particular cases. To answer for any correlator, any operators, I wouldn't be that bold, but I hope everything will work fine, but no guarantee. Okay.
Except for d equals 4, you don't have apparent any kind of picture like gamma deformation.
No, for d equals 4 we do have.
Except for d equals 4, you don't.
Except for d.
You don't have such a picture.
Precisely, we don't have, yeah. But we hope that this is a conformal theory, and I can only motivate it on particular calculations of 2-point functions. For example, for 2-point functions, I'm pretty sure that they will be conformal for local operators. But for 3-point functions, I'm not so sure. Even we had some attempts with Joao, with sort of, we couldn't answer some questions. The calculations have been tedious about 4-point functions, say. Okay, but at least I want to motivate this integrability for at any d. Sorry, 2 minutes more. At any d for this kind of local operators with magnons. So as I said, it can be, if you put Lm to 0, you have this kind of, you have wheels of this kind. And if you have the mixture of both, you have various multi-spiral graphs. Now, how to describe this graph? The simple idea is to take this sector, which can be considered as an operator which sends the points, integration points, this, and that, to this, and that. And then raising it into power of the length of this wheel, tracing it, you get the answer. Yes, but you have to take this particular operator in the space of coordinates. Yes, you have coordinates for d-dimensional coordinates in each point. So this is essentially this we call the graph building operator. This sector, this line, and these propagators, and you have to diagonalize it in order to find the trace at any L, and that will give you the answer. So we do it easily for single one. Suppose you have only this sort of one of these frames. The function is just the power times some spherical harmonics, and the eigenvalue can be easily calculated by plugging it in. In 2 dimensions, it's already a hardcore integrability to do it. Say you have 1 and 2. I mean, this is the picture. You have this operator. You send this to this point is fixed, the origin, and you send this to x1, x2 into y1, y2. You want to diagonalize this operator. And here is the structure which diagonalizes it. I don't want to give you a formula. It's very bulky, but it's simply you multiply all these propagators with given powers. These are the inverse powers of propagators. Then you act by certain operator of derivatives, symmetric traceless operator in each for 2 directions on the light cone n or n prime. This creates spins. You have to find it with spins also. And eigenvalue is just product of these 2 eigenvalues. And U is the spectral parameter, which appears just as a arbitrary as a label of eigenvalue. And okay, and then you do the following. You want to send. You want to see the asymptotics of this. Here you have integrations. So you have these 2 points open. You have 2 integrations, and these 2 points are fixed at 0, at x0. Then you want to study the. You want to consider this x1, x1, x2 as spins in some radial direction, and they can be placed in the radial direction on X space, and you want to consider x1 much larger than x2. They are very separated. And you discover here in this wave function of two spins, you discover S matrix, R matrix of Zamolodchikov. So you have sort of plane wave along radial direction with some momentum u1 or u2. The exchange gives you the S matrix of Zamolodchikov. So you can consider it as two spins which have the scattering matrix along the radial direction. And for any n, in principle, you can restore the whole function, and the eigenvalue is the product of eigenvalues. And to finish, I only want to say that you can, since you have this S matrix, you can do out of it the thermodynamical beta ansatz to solve the whole problem. I mean, I don't want to bother you with details, but you can really restore, you can write the thermodynamical beta ansatz, which solves the problem for wheels or even for spirals, a set of equations, which can be encoded into this Y system structure. And so, in principle, the problem is solvable for any of such multi-Magnon operators. The last curious comment is that if you do in this system what we call particle-hole duality, that was noticed by Basse and Zhong, that if you do such duality, you obtain from this model a sigma model on ADS D plus 1 sigma model, essentially. And with the S matrix equal to S matrix of Zamolodchikov, O 2 plus D, so it's strange because this is the matrix for compact spins, but but the dispersion relation is different. Instead of relativistic massive particles like in the Zamolodchikov model, you get this lattice-like structure, lattice-like dispersion relation, gapless, and this is supposed to be the sigma model describing fishnet graphs. So it's the model which looks very much like Zamolodchikov ON, but with a different dispersion relation. We can compute, for example, the asymptotics of very large fishnet graphs at any d, or rather reproduce the formula of Zamolodchikov. Okay, so that's the end of the story. Maybe I wanted to speak about correlators, but 4-point functions, but no way to speak. I only wanted to say that even in this dynamical fishnet, the 4-point functions for shortest possible operators, which are given by this kind of graphs, can be solved exactly. And here, by the way, the conformality is obvious. For this kind of simplest 4-point functions, they really are conformal, as they are characterized by length 2, essentially, operators. Okay, and here are some other results and prospects. Maybe you just can read it, but I don't want to spend more time of your time. Thank you very much.
Summarize which graphs are computed. So the wheels are computed, and like the bricks are computed. Those are the things.
Essentially, what is nice to compute, where you really can use integrability in its most powerful form, is all the graphs with cylindric topology. It could be just wheels with open ends. Not everything is computed. For example, if you have 3 lines with you have 6-point correlator, 3 into 3. This is still a problem to solve. You have to diagonalize this. So this looks like a spin chain which you simply evolve in the direction of cylinder. Yes, you grow the cylinder. But once you have multi-point functions, apart from these simplest ones which I flashed in the last transparencies, it's already a complicated problem. Some progress have been done by this conformal, by Basso, Caetano, and Fleury. They computed some structure constants for fishnet, and it also looks like conformal, by the way, some particular structure constants. Okay, but if you want really multi-point to compute efficiently multi-point function, you probably have to solve the problem of separated. You have to find separated variables for these non-compact spin chains. To glue various spin chains, say 3 spin chains together.
Any other questions for Volodya? And if not, I remind you, those who want to come to dinner, 5:30.